All right. Good morning, everyone. How's it going? Good. All right. You guys ready to get started? Don't get too excited. Today we're doing part 4, surface stresses and how it increases with depth. Last class, we talked about point loads, line loads, all that fun stuff. Today we're going to be reviewing that 2-to-1 method with an example. That 2-to-1 method where we are assuming the cross-sectional area that the load is being distributed across is increasing at a slope of 2-to-1 with depth. We're going to review that. That's really important because that's on your FE, maybe your PE, and it will be on your final. So make sure you're familiar with that. And then we're going to look into some other techniques using the fancy Busanesque guy and all that fun math and all the tables and stuff. So yeah, as far as like where we are in the week, just keep updated with the semester fast or quickly approaching an end. We're still April 21st. Yeah, we're still on set. Our exam will be in 2 weeks. And homework 4 solutions have been posted now. I'm not going to review those in class just with the time constraint and everything. So please review those on your own and let me know if nothing makes sense or even if a little part isn't making sense. I can explain it in more detail. I've already got some questions on Lab 9. So thanks for you guys who are like ahead of that. Please don't wait till the last minute to do that. If you have questions, let me know. I'd be happy to answer or like clarify anything in any of the websites or programs that we're using. But yeah, I mean, you guys all know this isn't your first semester. Like the last week and the last couple of weeks just gets crazy. So anything you can do to start chipping off some of this work that's going to be due at the end of the week, then that's just going to be super helpful, and it won't make your last couple of weeks not suck as much as they will. So any questions with where we're at? What? Yeah. Yep. Wait, or is it Monday? Yeah, no, it's a Sunday. You know me. Don't ask me about dates. It's in May. I know that. That's about all I got. Yeah, it should be due at midnight. But okay. One last thing. It's the most wonderful time of the year. Do you guys know what time of year it is besides finals? Yeah, ISQs. Remember this stuff? You guys already know all this stuff before. Please submit them. It's really helpful for me as still junior faculty teaching this class, knowing what went right and what I can do better in the future. I already know grading is something I need to work on. I'm sorry that the lab reports are taking so long to grade. But yeah, so please fill those out, and you guys know the deal, same as last year. The class response rate, I'm going to add extra credit points questions to the final that are reflecting of the extra or how much the class responds. That's all I see on my end until the end of the semester. It's still, again, 100% anonymous. I don't see names or anything. But right now I see 23% of the classes completed it. So thank you. So where we are right now, 2.3 points of extra credit questions will be on the final. So the more you guys complete it, everybody who's not here right now, then the more extra credit questions we'll have on there. So please and thank you for completing all that stuff. All right, we're sticking around in the same spots. Stress distribution in chapter 10, and then that DOS textbook. Has everyone been able to at least see where that is and download it? No issues there, like reviewing that. Again, like these images that are in this lecture and last lecture are all just screenshots from that DOS, like little PDF. So all the table numbers that are referenced there are the same table numbers in that. And just make sure that you're able to recognize where those things are and that you're reading the correct table, because that's really important. All right, so where we ended on Monday was talking about, or Tuesday was talking about the stress distribution of area using the 2-to-1 method. So we first, again, talked about the point loads and using Busanesque equation, how the stress in the soil is increasing due to loading on the surface. And it would make sense just, logically that directly underneath the point load, we have a higher increase of stress, but as we move away radially away from that point, we see that value starting to dissipate. Same with depth, right? The further away you get from the point source, the less you feel that point source. So the 2-to-1 method is a little different because this is an empirical approach. So it's not based off of a fancy, elastic media governing equation, mathematics, no differential equations there. And what it does is assumes the area, or I'm just going to say area, increases with depth. At a slope of 2-to-1. That's why it's called the 2-to-1 method. So for every 2 feet down we go below the footing or below the source, we go 1 foot out. And so that happens on both sides. So what we see is, of course, as the area increases, the stress decreases, which makes sense because we are getting further away from the point source or from the surface load. And this is because our stress is equal to our load divided by the area. So the load stays the same. We're assuming this P that is occurring at the surface is being transmitted the entire depth. So the P at the surface is equal to the P at 20 feet down. The only thing that is changing is that cross-sectional area. So as the area increases, since it's in the denominator or whatever that is, then the stress will decrease. So the equation that we showed is this delta sigma Z, which again is the increase of stress at any depth Z. Why'd you do this? Come back. Okay. Increased stress is equal to this Q naught, which is the stress at the surface times the width of the footing times the length of the footing, all divided by the width of the footing plus whatever depth we care about times the length of the footing plus whatever depth we care about. Sorry, don't put a square there. Don't know why I did that. And we also said that this is equal to Q times P, or B times L is equal to just the point load. So depending on what is given to you, it might be easier just to use this relationship, but they're exactly the same. You can transfer this because, or I should say because Q naught is equal to P divided by the area, which is equal to P times B L, right? This is if we have a rectangular footing only. No, don't do that. Come back. So it's a little hard to visualize. I know when I was first learning this, for some reason, it just was hard to stick, especially at 8 o'clock in the morning. So let's look at an example. I tried to draw this in 3D to kind of illustrate it a little bit more because it's hard looking at just a cross section of it. But okay, so let's say in this example, we have a structural column load that is carrying 20 kips. So this column load is what? Is it a P or a Q? P, yep, capital P. So this is just a load because it's in kips. That kips is just 1,000 pounds. It's going to be, that column load is going to be distributed across a 5 foot by 5 foot footing. As planned to use a particular column. And we're using the 2-to-1 method. What would be the increase of stress at 15 feet below the foundation? So this is at Z. It's that Z equals 15 feet. Again, kips is 1,000 pounds. So what we have here is 20,000 pounds is that P. And so this is our column. And again, this column, instead of just going straight into the soil, we need to distribute this laterally or horizontally across a footing. So this B is equal to L since we have a square. And at the ground surface, what we're saying is that at a depth of 15 feet, this surface area that is normally 5 foot by 5 foot is now going to be much larger, right? It's going to have a larger surface area. So this surface area is going to have a slope of 2 to 1. So that's kind of hard to draw here, but again, for every 2 foot down, we go 1 foot horizontally. But the P is staying the same. So that P, that 20,000 pounds is staying the same. So this stress at the surface is Q naught, right? Because Q naught is equal to P divided by B times L, the original load divided by the surface area. But what we want to see at 15 feet down is this delta sigma Z. So this is our delta sigma Z down here, which is the P divided by this new larger cross-sectional area. So again, we had this equation using the 2 to 1 method. So we can plug everything in. Again, this here is really just P, structural loading. So we'll keep all our units to make sure that we're doing the right ones here. So this is 20,000 pounds divided by B plus Z. So 5 plus 15. And then luckily, since it's a square, this is the same thing. So 5 plus 15. So this is in feet. This is in feet. So the whole thing is going to be in feet squared. Yellow is not a good color to use. So this delta sigma Z at 15 feet is equal to 50 pounds per square foot. That means if we were hanging out down here at 15 feet below the footing, we would not feel the 20 kips loading. We would feel 15 pounds per square foot. So again, though, what I mentioned last class is this limitation is saying that this 15 feet or this 50 pounds per square foot is everywhere beneath the footing. So right here, directly underneath that center of the load, you could probably imagine that this would realistically have a higher pounds per square foot. You'd feel more stress out on the edge of this, right? But for this method, unfortunately, we have to assume that the entire area, so assume is the average delta sigma Z. So I mentioned last time too, and I kind of drew this, like realistically, if we were to plot this stress increase across this area, we would see something like this, where sorry, that was really bad. Something like this, where the inside, closer to that column footing, we see a higher increase of stress. But realistically, what this method is doing is just taking the average of everything. Taking the average of this. Think about when we want to use this layer. Like this technique is used when we are generally analyzing an entire layer or some large surface area object. If we want to pinpoint in and try to measure the increase of stress at like a tunnel or a utility line or some like smaller object compared to the footing or the building that we're putting on top of it, then this method really isn't as accurate, right? Because this is just showing the average on this giant area. We care a little bit more about a certain layer. So this is used in analysis of like entire soil layers. So if we want to know, or if we like say like 30 feet down, we have a clay layer that's through the entire project site. or let's just say an organic layer, right? We have a nasty organic layer that has, compressibility issues, water issues, all this stuff. And we want to know what the stress level is on that entire layer due to the footing. Then we would use this because this is the average. Now, if we had just an isolated pocket of organics, like I don't know, somebody in like the 1800s just dug a pit and filled it with organics, then this technique really wouldn't provide that much insight because we're like looking at a smaller area, and instead this is showing the average across a larger area. So this assumes, the entire area is averaged. It also assumes that this is a rigid footing. Now we won't get into the differences between rigid and flexible footings too much in this class. That's going to be the design analysis of foundations. But although like in our mindset, a footing concrete is going to be rigid and it's like, a stiff material, some footings are more stiff or more rigid than other footings just based on the reinforcing and stuff. And so the way that stress is applied to the surface actually changes. You can probably picture like if you took a piece of paper on a table or put a piece of paper on sand or something and then pushed on that piece of paper, you would see bending in the footing and you would see the stress being isolated underneath that where you pushed, right? Now, if you took a coaster or a piece of plywood and applied the same stress, that footing or that plywood is going to be more rigid than the paper and you would see a different distribution of stress. So this is like still a kind of a more deep phenomenon in geotechniques, but this technique again assumes that this is a rigid footing where a lot of times our theories like the Boussinesq theory, that's all derived based off of a flexible footing because it's a little bit more realistic. All right, so 2-to-1 method. There'll be more examples, for this and everything. But let's say instead of finding the average delta sigma z, we need to a little bit more accurate and more pinpoint something underneath a discrete area. So what this was first derived as is a rectangular loaded area. Again, this is going back to Boussinesq. But the way the math checks out is that this is easier to derive under the corner of an area. So if we have a footing, and this is just like, I don't know why it's highlighted like this, but a footing with a width and a length of L and B, just like before. And this is uniformly loaded. So we have this Q, which is equal to the load divided by this area. If we want to find the point or the increase of stress at a specific point, then it was first derived for looking at the corner of this area. So either here, either there, under the corner of it. So from Boussinesq, what we're assuming here again is that this is elastic media and that now though, this was derived for a flexible foundation. So the 2-to-1 method is derived for a rigid foundation. This is derived for a flexible foundation. And again, like if you're planning on going into geotechnical engineering, or if you are taking my the class next semester with me, then just kind of put this in the back of your brain because we'll talk more about the difference between flexible and rigid foundations in that class. So this is the fun math equation that we get to derive from it. Again, Boussinesq, anytime you think of Boussinesq, think about like crappy math and all this stuff. But luckily, again, we have a function that we can change this influence value by using relationships of the geometry and the depth that we care about. So just like before, we're saying that that delta sigma z, that increase of stress, is a function of the stress at the surface. So Q naught, just say Q naught at the ground surface. And then we multiply that by an influence factor. And just the way your textbook shows it, this is the third influence factor that they talk about. So that's why they have I3. So I kept all the terminology consistent. So when you look in those notes that I uploaded from the textbook, you'll see that it's I3. That's this one here. So for this is all in table 8 or 10.8. And I provided some of those tables here, but let's first see what it's a function of. We see here, there's M is B divided by Z, and N is L divided by Z. So for this, if it's a rectangular a property, then our L is always going to be greater than the B. So that's going to be the one that we choose here. So if it's a square, B is equal to L, good, just choose whichever one you want. But if we're given rectangular properties, the L, the length is always going to be the larger of the two that you're given. So you wouldn't be explicitly told that B is equal to this, L is equal to this. You give the dimensions and have to use the L is greater than B. So this is what the table looks like here, and how we would read this. Again, what these values here in the center are the I3 values. So everything is the I3. So let's say we had a Q naught, so a loading at the surface of 800 pounds per square foot, and the L and the B is a square, so it's equal to 5. We want to know at a depth of 15 meters or 15 feet. So what we would do is this M and this N are actually equal to each other since it's a square. 15 or 5 divided by 15 is 0.333. So what we would do is read where these actually are. Our M values, 0.333, would be here. And then our N value would be here. And I mean 0.333, so technically you would interpolate it just a little bit or round up. The value should be somewhere in this area. And we would see that, again, this delta sigma Z is equal to Q naught times I3. So this would be our I3 value. So let's just say it's 800 pounds per square foot, and then somewhere around 0.0374. I'm just going to use that one. So this means our increase of stress is 29.9 pounds per square foot. So if you notice, this is actually the same dimensions from the 2-to-1 method. 5 by 5 feet, 15 feet down, and 800 pounds per square foot. So comparatively, that one, so from the 2-to-1 method, right? We said this was 50 PSF. And now for this under the corner, we can see that our delta sigma Z is 30 pounds per square foot, right? 29.9, just rounding up. You can already see, like, this is the corner. This would make sense because we're further away from the center of our load. But you can see why, like, if we were using the 2-to-1 method, we would assume the entire thing is at that 50. So the interesting thing is this corner, area of the corner, we can actually use this to determine the area of the center of it. As most of the time, that's where we would assume the larger amount of loading is going to be. So although the math is all derived for the corner, all we need to do is assume that there are 4 areas surrounding it. And now if we analyze each area in the corner, that then becomes the center. So I know it's early, but again, think about this like logically. Like, we have an area where the analysis is under the corner. If we just have the same area and rotate it 90 degrees each time, so we have 4 total areas now, and we add all of those analysis with this larger area, and we're still analyzing all those in the corner, then it now becomes the center. So this requires looking at our footing and actually shortening the sizes, so dividing the length and the width by 2, so we can analyze it for just one quadrant of our footing. Good question. So it depends, because the stress, if you're given like the P, then yeah, but the area that you're loading under is I mean, it's a smaller area. So yeah, you're looking at each one individually. So that area is smaller. You're dividing in the length by 2. So what it actually looks like then, is if we had and cared about under the center of the rectangle, then we would still have our Q naught. But now what we would do is multiply this by I3 for one, and then plus I3 for the second one, plus I3 for the third one, and then plus I3 for the fourth one. So again, our one, this would be our one rectangle, 2, 3, 4. So as you can imagine, this is probably a really common thing, right? We care about analyzing it under the corner or under the center of the footing. So this was already previously derived. Instead, now we just say all of these influence factors can be combined into I4. So now we're moving on to the fourth influence factor. Again, it's only called I4 because of the textbook that we're using, I subscript 4. It's just the fourth influence factor that we come across. So if you look at it on any other websites or any other, textbooks or something, it might not be called I subscript 4. It's just specific to our textbook. So yeah, so the important thing is again, if we're given under the center, what we have to do first is recognize that if we are subdividing it into 4 quadrants, then we need to divide the B and the L by 2 each. Because in the problem statement, you'd just be given a large B and L. And if we wanted to subdivide it into the 4 I3s, then we would have to do that. But for the I4, then we just use the large B and L. So for that, it's the same thing, except now our N1 and M1, they have little subscripts under them just to distinguish before the previous ones. Are now N1 is a function of Z divided by B divided by 2. So all of this is found in table 10.9, which is right here. Again, this is under the center of an area, and the function that we would be using is delta sigma Z is equal to Q naught times I4. This is our I4 here. So let's look at the same example. So our Q naught is 800 pounds per square foot. Same example before where we care about 5 foot by 5 foot. So again, there's 2 options. If we care about the center, we can either use the I3 values. And if we use the I3 values, then we need to divide the B and the L by 2 because we need to look at each one as a separate quadrant. Or we can use the I4 values. And if we use the I4 values, then we just look at the entire footing. So big, like B is equal to L, which is 5. So for that, M1 is L divided by B. And then N1 is Z, so 15 feet, which is equal to 6. So we can find 1 for our M1 is here. And then N1, 6 is here. Just kidding, is here. And so wherever these intersect, this will be our influence factor. So our I4 equal 0.051. So if we actually do this math out, our delta sigma Z Q naught, what we would see is this equals 40. Let me make sure I got it right, 40.8. So what does this mean about the 2-to-1 method? Think about like our 2-to-1 method. This was the 2-to-1 method. What was the value that we got from that? 50 pounds per square foot, right? So this is a conservative method because now using Boussinesq, we're under the center of our footing, right? Like, so this should theoretically be the max value. But Boussinesq, since it's based off of a like theory of elasticity and actual like analytical equation, what we see is we actually have a lower value. So our 2-to-1 method provides a rough estimate that is over the typical actual value that could be that the soil could be being felt for. So 2-to-1 method is generally a conservative, which means we are overestimating. So our design is over like strong, if or whatever. That's not a real term, but you guys get the point, hopefully. So yeah. So again, this is using those two methods, we can basically find the area anywhere within like the domain underneath the footing, right? Because we can divide it, we know under the center, we know under the corner. If we have something like still in like, right here, that is still under the footing, then we can divide it into different rectangles, like this. Now we have 4 ones and we can add them up using the I3 value. But what happens if we want to use Boussinesq and we want to find it off the center of the area? So now out of the original scope of the area. So again, I'm sorry, it's 2D. I wish I could have a 3D model to represent this a little bit more. But we have the depth, of the area footprint on the surface. This is what it's shown here. So now what if we need to analyze this area, let's just call it A, that is off of our original area. So now we're going down and we're going away from the perimeter of our footprint of the footing. So what we actually would see is, use a different color. So yeah, at the depth that we care about, we're actually off of this footing surface area. And you guys are probably getting where, or some of you are probably seeing what we're going to do here. So if we visualize this footing as, top view here, and what we're actually looking at now, if the point that we care about is a distance X away from our footing. So this is a bird's eye view looking down. Then how we actually analyze this is we assume a larger footing area, and it's under the corner, which is easy. And then we subtract out this footing area that actually doesn't have loading associated to it. So we have to use the fun geometry stuff and try to make sure that the shapes line up so that we have some way of analyzing it. So either under the corner or under the center of our rectangle. And using a combination of these, like subtracting out areas, like false areas, then we can find the stress increase. So again, we have this real area plus the false area, and then we subtract out this false area. So just for the sake of the colors here, what I'm going to show is, so our delta sigma Z, the gray, which is the one we actually care about. So this is our gray, is equal to the delta sigma Z of our blue. This is our blue, minus the delta sigma Z of our red. Was everyone seeing how we can do this? I think the technical name is a pseudo area. I don't know why we like to use that. Just people like using it's a pseudo area. It's a false area, and we are modeling it as if there's something here. But if we subtract that out through another analysis, then we get a representation of the actual stresses there. So let's look at an example of this real quick. So off-center example. So same thing before. This is the bird's eye view. We have a 2 meter by 3 meter, which means what is our B going to equal? Two meters, which means our L is 3 meters. That's a really important step. The L is always larger than the B. So make sure if you set those wrong, then the whole math doesn't check out. Okay, so we have Z at 4 meters, so that's going into the screen. What is the delta sigma Z at this point? So what we are going to model this as is this larger area, because this is our pseudo area here. This is the point we care about. This is point A. So we add this 1 meter on of a false area. And then we subtract out that false area, that 1 meter, right? And our point A is right here still. And again, since we're working in stress, then luckily that doesn't change. Now, if we were only looking at the P, the load, then that will change because we are changing the cross-sectional area. But whenever we're in stress terms, pounds per square foot or KPA or something, that is like normalizing it against any type of area. So we don't need to change that Q value. So what this is the delta sigma Z, the one that we actually care about, is equal to, I'll just say, call this one, instead of using colors, this one 1, and then this one 2. So what we would do is look at the table 10.8, which is the rectangular area corner. And so for 1, our M and N, this is B divided by Z. So again, our Z is 4 meters. So B is 2 divided by 4, which equals 2.5. And then our N for our first circle is L divided by Z. So that is 3 divided by 4, which is 0.75. Sorry, guys, this is not right. This should be 4 because this is for the first one. So our L is 4 since this is our fake L. That's really important. Yeah, so 4 divided by 4, so that's 1. So now for 2, for the second, the red one, our M is L divided by Z. What's our L now? Yeah. So our B is now 1. So this is now our new B, and this is our new L. So because of the geometry, we have to switch that. So our M is B divided by Z, which is 1 divided by 4. So that's 0.25. And then our N is 2 divided by 4, which is 0.5. That's really important. The distinguishment between B and L, when we divide these areas up, that might change. So the L is always going to be the larger one. All right, so what we would do now is flip over to table 10.8. And again, this one is our I3 value, since we're looking at under the corner of the footing, not the center. So we look for our I3, make sure that you're reading the right one. I3. And what we had from before, so for 1, and then for 2. So for our first one, we had 0.5 as our M value, and then 1 as our N value. So this means our I3(1) is equal to 0.1202 right here. And then for our 2, oh, oops, I wrote over it, my bad. You guys see it then. So for this one, since it's 0.25, we would need to interpolate between these 2 points right here. So since there's a pretty much large gap, we just linear interpolate between these, and we see that it is 0.0473. So there's a lot of estimating here, right? Like there's a lot of assumptions. We're assuming that it's elastic media. We're assuming all these things. This is an analytical approach to estimate a real world thing. So don't stress too much on interpolating like super accurately with these I values, right? Because like, again, there's this discrepancy between analytics and what's actually happening. So if you have a time where, like in the previous example, where let's say it was 0.55 or something, like something in between, then don't try to worry about like double cross interpolating. Just interpolate between one of them and then try to get like a good estimate in between those two. You know, it's okay to estimate with this, even though they show it to the 4 decimal places. We just can't be that accurate because it's math using to define real world stress loading. All right, so what this would actually look like now, we have all these values. Our I values, what were our I values again? We had, this one was our I3, 1 was equal to 0.1202. And then this one, our I3, 2 was equal to 0.0473. Delta sigma for the real one equal to 150 kilonewtons per meter squared, since our Q is the same for both, times 0.1202. We subtract, since we're adding out this, taking out this area, 150 kilonewtons per meter squared times 0.0473. And so that equal means our delta sigma Z is about 10.9 kilonewtons per meter squared. You can probably see the way this equation is set up. If everything is in stress terms, so if everything's in Q, then really we could just pull this off to the side, right? Out of our, we could pull this out of our function and we could actually set up an equation that looks like our Q is equal to our I3, 1 minus our I3, 2. So that's the benefit of this technique, right? So do whichever one you feel more comfortable with. If you're new to this, then I suggest looking at each square and analyzing the delta sigma Z to each one respectively, instead of trying to take it out, you know, and simplify it that way. But you can always check your work that way to make sure that the math is checking out. So there's different ways of viewing this. You'll see in the textbook, there's the table format, right? And this is the variation of I3s here. But depending on what book you're looking at, you might also see something like this. So this is like this reading the same thing. So these are like nomographs or some way of showing a bunch of numerical data and the trends on it. So knowing how to read these, like this would be really important, because this table, for example, or instead of showing the table on your FE or your PE handbook, then they might just give you this graph. So I'm sure by now everyone knows how to read these, but let's just recap. Again, the x-axis is in log scale. So we've talked about this before, like make sure you're reading these tick marks correctly. Point, you know, this is between 10 and 1. So halfway is not right here. You know, you have to like actually read it in log form. So let's say for this one, this example, we have an I3 of 0.081, and that is at 0.6 M and 0.4 N. So what we would do is we'd find 0.6 M. So this is 1 point, or let's start at 0.1, I guess. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So that's our 0.6 right there. And what we would do is read this each one of these contours represents our n value. So our 0.4 n value is this contour right here. So what we would do is we would read this up wherever it intersects with this contour. Just imagine the line deflecting and going straight to the y-axis. And that y-axis is our I3 values. So, I mean, you guys have seen these charts before, right? Like Reynolds numbers and all that fun stuff. So I'm just, if you're unfamiliar with knowing how to read these types of data, this is basically like, engineers love language here. Like they just love showing stuff like this. So it's really helpful to know how to read these. So 0.8, we see that it matches out with the table. Of course, with the table, we can be a little bit more accurate, but then again, like we're talking about relating analytics to something that is real life loading. So being super like hyper accurate doesn't really make much sense, so we don't need to be too accurate with that. All right, so what we've covered now is rectangular loading. Now, although rectangular loading is much more common, who thinks why rectangular loading is more common for like structures and stuff? Anyone want to take a guess? Yeah, exactly, right? Like with 2x4s come in straight lines, not in circles. So it's just practically, it's much easier to build a footing or a structure with right angles for measuring and also for just, the practicality of pouring concrete. Now, sometimes though, like some footings are circular, like water tanks, we see like just for the clarifiers and all those fun water tanks that have fluids in them, it's easier to have laminar flow if it's circular or something like that. I'm not a hydrologist, so I don't really know. But also we have footings like sometimes that are large enough, like this octagonal footing. Sometimes it's easier to model this one as an actual circle, So sometimes even though we use straight lines, like if we have enough smaller straight lines like an octagon or a hexagon or something, then it's easier to model these as a circle. So techniques using Boussinesq were still derived for circular loading, although it's not as common in geotechnical like foundation design. We still have areas where we would need to determine the stress increase under a circle. What's up?
If you're doing like an octagonal area and assuming it's a circle, do you use like an inscribed circle or what's the name? Where it's like
the concentric or you would usually use an average, or it depends on the project. You would underestimate, because if you underestimate the area, you increase the stress. So if your problem is like if you're unsure about the loading conditions, then it'd be safer to underestimate the area. If you're pretty confident, then you would use the average. So you wouldn't do the outer circle, you would like connect the points on the interior or something. But yeah, good thinking. It's all going to be project specific and how confident the engineer is. So for this one, the equation's a little bit more gnarly here. So there's actually two tables. I'm not even going to show the actual like analytical equation on there because it gives me a headache and PTSD just looking at it. But what they do is now we need to find two functions. So what we see is we take all this crazy math, and instead now this delta sigma z is a function of still our q, which is the surface loading, p divided by a, but now this area is the circle. Instead of influence factors, they got a little bored. Instead, now they're using coefficients. So a plus b. So to spice things up a little bit, they used a and b's instead of counting i's all the way up till 20. What we see is a is a separate function. Again, this sideways or fancy looking f, that's just a function of z divided by r, where r is the radius of the circle. I should say capital R. And then b prime is a function of lowercase r divided by uppercase r. So from here, lowercase r is the radius to the point of interest. So make sure to make those two distinctions. Uppercase R is the actual structural load, our footing, our water tank, whatever. That's like physically what is there. Lowercase r is that theoretical radius to whatever point we care about on the ground surface. So A and B, now we have to find two things. So that means we have to reference two tables. So that's tables 10.6 and 10.7 in your DOS notes. DOS notes. So to find A prime, again, that's this first one. Again, it's a function of Z divided by R. Oh, and R divided by R. So both of them are a function of each other. So for that, again, we would read the intersecting point. So if we had something here and had something here, we just read wherever they intersect. And then to find B, then we would have the same thing. So this, make sure you're always reading the right charts here. B prime and A prime, so make sure you're reading the right one. So again, there's table forms like this one, but there's also the nomograph forms. I think it's a nomograph. Has anyone heard that word before? Am I saying that right? I don't know. It's an old person term, I think, but nomograph. So let's look at an example of this one real quick. So similar numbers to our 2 by 1, that we were doing before. So 800 PSF, radius of 5 feet, and now we're finding it at a depth of 15 feet. So where we actually what we care about is this point is directly under the edge of it. So that's, our lowercase r is equal to our uppercase r. Oh, I'm sorry. No. Under the center. So we find the increase at the center and along the perimeter. So we're doing two cases here. So first case, what would be our lowercase r if it's under the center? 0, good. And then 2, our lowercase r would equal, if we care about the perimeter. So now it's this point here. The lowercase r would equal our uppercase r, which is 5 feet. Okay, so what we care about here, let's look at our center. So our first case, our center. So this means our r is 0 feet. And so this is our z divided by r. Our uppercase r is 5 feet. Sorry, 15 feet divided by 5, which is equal to 3. And then our lowercase r divided by our uppercase r is 0. 0 divided by a number. So that's the first case that we care about. We also care about the perimeter. In this case, our lowercase r is equal to our uppercase r, which is 5 feet. So our z divided by our uppercase r is the same. And then our lowercase r divided by uppercase is going to be 1. So we have these two values. Now what we need to do is look at our tables. So for our center, we care about a point that is 0 and 3. So I'm just showing like this is z divided by r and r divided by r. That's what those coordinates are showing, so 0 and 3. So that's right here. For our perimeter, it's 1 and 3. That's right here. So our A, now I'm using the C subscript for center and P subscript for perimeter. Those are those two values taken from our table. And now we would put these aside. This is our A functions. So we need to go to the next table, table 10.7, to find B. we do the same things before. So for our center is right here. For our perimeter is right there. So putting those aside again, BC is for the center and BP is for the perimeter. And now we can do all the fun math. So we have these functions here. We know that our delta sigma z is equal to the Q times area plus, or A plus B. So for our center, £800 per square foot times 0.05132 plus 0.09487, since we're at our center here. Is equal to 116.95. So the perimeter delta sigma z is equal to, don't forget the 800 pounds per square foot. And then this is 0.04487, and then plus 0.07325. So 94.5 pounds per square foot. So the interesting thing here is our circle, remember, like same stress load, like similar dimensions. Like remember when we did the 2x1 area, we had a 5 foot by 5 foot radius, or 5 foot by 5 foot footing. So something like this. You know, this was like what we did for the 2-to-1 method. Remember, under the average value for that was 50 pounds per square foot. And so now we're getting 116.95 pounds per square foot. So what could we say about all of these techniques? You know, we've kind of looked at the same thing, 5 foot by 5 foot, 800. Like all of these techniques, would you say they're all pretty, like you would be confident using all of these techniques as an analysis, right? Yeah, probably not. I'm seeing some like shaking faces and stuff, right? So like the most important thing that like we can't teach in this class is like the discernment of what analysis technique you need to use. And that's strictly based off of like the severity of the project. So again, like if you have like low loading and you just need to like, you know, you're pretty sure that the site conditions are pretty consistent, you're confident that the soils is there, you're confident that the structural engineer knows what type of loading there is and it's not going to like deviate too much, then this type of analysis is okay. You know, like if you have some settlement or you have some issues, it's not going to be the end of the world. But if we actually have like a very sensitive project, again, like the power plants, the dams, the things that are supposed to last for decades, Amazon facilities, like that kind of stuff, then we would always want to do some type of field verification. So actual numerical modeling or actual stress plates, so sensors in the ground that can actually measure the loading to ensure that our analytical and our like estimates on paper are what they actually are in real world. So it's always going to be based off of the project that you're working on. And you can see firsthand, like just from these examples, like the values are all over the place. So you can get a good rough estimate, but nothing beats actually like boots in the dirt and figuring this out realistically. So that's what we're going to start covering next week a little bit. We'll still do a little bit, like one more example of stress increase from an analytical side of things. But then we'll start looking at actual like stress, like field measurements and how to determine the stresses from real world applications, not just on paper. If you haven't collected your tests yet, please come by here.
takes a test and then isn't really curious, like find out.
I know, I'm surprised.
They know what they got.
Don't you want to put it on your fridge?
I